They were loud, they were powerful, and for a brief moment in history, they looked like the future of rail transport. From high-speed passenger trains racing through the French countryside to massive freight haulers thundering across the American West, gas turbines promised a new era of speed, efficiency, and technological progress. These machines combined the brute force of jet engines with the practical needs of railroads, creating some of the most ambitious and experimental locomotives ever built. But the dream didn't last. Today, turbine-powered trains are largely forgotten, relegated to museum displays and the memories of engineers who believed they would revolutionize the industry. What happened? Why did such a promising technology fade into obscurity while diesel-electric and electric trains continued to dominate? This is the story of turbine-powered trains, their ambitious beginnings, their brief moment of glory, and the hard lessons that ultimately grounded them. It's a story of innovation, economics, and the unforgiving realities of engineering. Welcome to the rise and fall of turbine-powered trains. To understand why railroads became fascinated with gas turbines, we need to step back to the years immediately following World War II. The late 1940s and early 1950s were a time of tremendous technological optimism. Industries around the world were obsessed with turbines. Aircraft manufacturers had just perfected the jet engine, fundamentally transforming aviation. Ships were beginning to experiment with turbine propulsion. Power plants were installing massive turbine generators. The technology seemed to promise unlimited potential. Gas turbines offered several compelling advantages over existing power sources. They were remarkably lightweight compared to piston engines of equivalent power. They had fewer moving parts, which theoretically meant less maintenance and greater reliability. They could run on a variety of fuels, from kerosene to heavy bunker oil. And perhaps most importantly, they produced extraordinary amounts of power from a relatively compact package. For railroads, this was particularly attractive. The steam era was ending, and while diesel-electric locomotives were proving successful, they had limitations. Early diesel engines were heavy, relatively underpowered, and required complex cooling systems. Multiple diesel units often needed to be coupled together to haul heavy trains, which was expensive and operationally complex. The idea of a single powerful turbine locomotive that could replace multiple diesel units was incredibly appealing to railroad executives and engineers alike. There was another crucial factor: fuel economics. In the post-war period, oil was extraordinarily cheap, particularly in North America. Bunker fuel and residual oils, the bottom-of-the-barrel products left over from refining gasoline, were almost worthless byproducts. Turbines could burn these low-grade fuels efficiently, or so the theory went. If railroads could power their locomotives with fuel that cost pennies per gallon, the operational savings would be enormous. Even if the locomotives themselves were more expensive to build, the engineering appeal was equally strong. Turbines operated on a beautifully simple thermodynamic cycle: compress air, add fuel, ignite, and extract energy from the expanding hot gases. Unlike reciprocating engines with their pistons, connecting rods and valves, turbines had only one major moving assembly, the rotor. This promised smooth operation, high power output, and minimal vibration. For engineers who had spent decades wrestling with the mechanical complexity of steam locomotives and the growing pains of early diesels, turbines seemed like an elegant solution. Speed was another consideration. As passenger rail began to face competition from automobiles and airlines, railroads needed faster trains. Turbines could generate enormous amounts of power instantly, providing the acceleration needed for high-speed service. The jet age had captured the public imagination, and turbine trains seemed like the natural evolution of rail transport into this modern era. So, the stage was set. Railroads had powerful incentives to explore turbine technology: more power, less weight, cheaper fuel, simpler mechanics, and the promise of higher speeds. What followed was one of the most ambitious and expensive experiments in railroad history, spanning multiple continents and several decades. The question wasn't whether turbines would work on trains. The question was how to make them work better than the alternatives. The story of turbine trains doesn't begin with the massive locomotives and record-breaking runs that would later capture headlines. It begins much earlier, with small rail cars and experimental prototypes built by engineers who were willing to try something radically different. As early as the 1930s, Swiss engineers were experimenting with turbine-powered rail cars. These weren't the powerful machines that would come later, but rather proof-of-concept vehicles designed to test whether a gas turbine could practically propel a train. The Swiss experiments were modest in scope, but important in principle. They demonstrated that, yes, a turbine could move a rail car, but they also revealed the first hints of problems to come. Fuel consumption was high, efficiency at low speeds was poor, and the mechanical complexity was greater than anticipated. In Britain, engineers were thinking about turbines in the context of high-speed rail development. The concepts that would eventually lead to the advanced passenger train had their roots in turbine research from this era. British Rail understood that if they wanted trains to compete with air travel, they needed new sources of power and new approaches to speed. Turbines represented one possible path forward, though the British would ultimately pursue this direction less aggressively than their American and French counterparts. Germany, too, conducted turbine experiments before World War II, though much of this research was interrupted or lost during the conflict. German engineers, always at the forefront of rail technology, recognized the theoretical advantages of turbines and conducted early tests with small rail cars. These experiments were part of a broader German fascination with streamlining and high-speed rail that dated back to the Art Deco era of the 1920s and 30s. What's important to understand about these early pioneers is that they were working in an era when turbine technology itself was still developing. The jet engines that powered aircraft in the 1930s and 40s were primitive by later standards. Materials science hadn't yet developed the high-temperature alloys that would make modern turbines possible. Manufacturing techniques were less precise. Control systems were mechanical rather than electronic. These engineers were essentially trying to adapt a technology that was itself still experimental. The early rail cars were typically lightweight, single-unit vehicles designed for passenger service on branch lines or secondary routes. They were meant to be economical alternatives to locomotive-hauled trains, capable of providing frequent service without the expense of a full consist. The turbine seemed ideal for this application, a compact power source that could be installed in a rail car without taking up too much interior space. But the results were mixed at best. While these early turbines could generate adequate power, they were terribly inefficient at the low speeds and frequent stops typical of branch line service. They were noisy, far louder than diesel rail cars. They required specialized maintenance that many railroad workshops weren't equipped to provide. And the fuel consumption, particularly during idle and acceleration phases, was disappointing. Still, these experiments weren't failures. They provided crucial data about how turbines behaved in railroad service. They identified the operating conditions where turbines performed best and worst. They revealed mechanical issues that needed to be solved. And they kept the dream alive, proving that turbines could work on rails, even if the early implementations weren't yet practical. By the 1950s, turbine technology had advanced considerably thanks to military aviation programs. Jet engines were more powerful, more reliable, and better understood. Materials had improved, and oil remained cheap, making fuel consumption less of a concern. The stage was set for turbines to move from experimental rail cars to full-scale locomotives and high-speed trains. The pioneers had shown it was possible. Now it was time to show it was practical. The 1950s through the 1970s marked the golden age of turbine trains, when the technology moved from experimental prototypes to regular service on some of the world's major railroads. This was the era when turbines seemed poised to reshape the industry, when the largest and most powerful locomotives ever built roamed the rails, and when high-speed trains powered by jet engines broke speed records and captured the public imagination. Let's examine the most significant turbine programs from this remarkable period. Union Pacific Gas, turbine electric locomotives. The most ambitious turbine program in railroad history belonged to the Union Pacific Railroad. Between 1948 and the early 1960s, Union Pacific operated a fleet of gas turbine electric locomotives that remain, to this day, among the largest and most powerful locomotives ever built. Railroad enthusiasts knew them by their nickname, the Big Blows. Union Pacific's interest in turbines was driven by a simple operational reality. The railroad moved enormous tonnages of freight across the vast distances of the American West, particularly coal, ore, and other bulk commodities hauled from Wyoming and Utah to coastal markets. These were heavy trains, often requiring multiple diesel locomotives coupled together to generate enough pulling power. Union Pacific saw turbines as a way to consolidate that power into fewer, larger units, reducing crew requirements and operational complexity. Working with General Electric, Union Pacific developed 3 generations of turbine locomotives. The first generation, delivered starting in 1948, were the pioneering units that proved the concept could work in heavy freight service. These weren't small machines. They produced around 4,500 horsepower from a single turbine, comparable to 3 or 4 contemporary diesel locomotives. But they were just the beginning. The second generation, delivered in the 1950s, increased power output substantially. These were the true giants. Union Pacific ordered units capable of producing over 8,500 horsepower. When operated in pairs, as they often were, these locomotives could generate over 15,000 horsepower, more than any other locomotives in the world at that time. To put this in perspective, modern diesel locomotives typically produce between 4,000 and 6,000 horsepower. Union Pacific's turbines were in a completely different league. The scale of these machines was extraordinary. They were massive, long, and incredibly heavy. The turbine itself sat in the center of the locomotive, surrounded by fuel tanks, electrical generators, cooling systems, and all the support equipment needed to make the system work. The exhaust system was particularly impressive, or perhaps intimidating. When operating at full throttle, these locomotives expelled jets of superheated exhaust gas that glowed visibly in the dark. The sound was unforgettable, a rising, screaming whine like a jet aircraft preparing for takeoff, mixed with the deeper rumble of the electrical generators. Union Pacific ran these turbines primarily on the Sherman Hill route in Wyoming and across the desert territories of Utah and Nevada. These were perfect operating conditions for turbines. The routes were long and relatively straight, allowing the locomotives to run at high, sustained power outputs for hours at a time. There were few stops, which meant the turbines could avoid the inefficient idle and low-power operations that killed fuel economy, and the arid climate reduced concerns about the extreme heat these machines generated. For a time, the economics worked. Oil was so cheap in the 1950s that Union Pacific could afford to burn low-grade bunker fuel that cost almost nothing. The turbines could haul more tonnage with fewer crew members. Maintenance, while specialized, was manageable. The big blows became icons of American railroading, symbols of power and technological ambition. France, the TGV 001. While Union Pacific was building the world's most powerful freight locomotives, France was pursuing turbines for an entirely different purpose: high-speed passenger rail. The result was one of the most significant trains in railroad history, the TGV 001. In the late 1960s, French national railways faced a dilemma. The country needed high-speed rail service to remain competitive with air travel and highways, but electrifying new high-speed lines was expensive and time-consuming. A turbine train offered an appealing alternative, a high-speed performance without the need for electrification infrastructure. The TGV 001 was designed as a testbed to explore this possibility and to develop the aerodynamics, bogie designs, and control systems that would be needed for trains operating at unprecedented speeds. Delivered in 1972, the TGV 001 was visually stunning. Its sleek orange livery and aerodynamic nose design became iconic images of French engineering ambition. Unlike Union Pacific's massive freight haulers, this was a lightweight, purpose-built, high-speed train. It had turbines mounted in power cars at each end of the train set, allowing for push-pull operation and quick reversal at terminals. The performance was breathtaking. During testing, the TGV 001 reached 318 kilometers per hour, or 198 miles per hour, making it the fastest turbine train ever operated. More importantly, it proved that trains could safely operate at these speeds with proper engineering. The data collected from the TGV 001 directly informed the design of the TGV Sud-Est, the electric high-speed train that would enter service in 1981 and establish France as the world leader in high-speed rail. The TGV 001 conducted thousands of test runs over several years, pushing the boundaries of speed, safety, and passenger comfort. Engineers gathered data on everything from track forces and aerodynamic buffeting to passenger perception of motion and noise. The train became a testbed for innovations in bogie suspension, braking systems, and structural design. It demonstrated that dedicated high-speed lines with gentle curves and minimal grade crossings were essential for safe operation above 200 miles per hour. Interestingly, while the TGV-001 proved turbines could power high-speed trains, it also revealed their limitations. Fuel consumption at high speeds was significant. Noise levels, while acceptable on test tracks in rural areas, would be problematic for service through populated regions. And the operational flexibility of electric trains, which could draw power continuously from overhead wires, proved superior for sustained high-speed service. The turbine had served its purpose as a development platform, but France's future would be electric. Amtrak, the UAC Turbo Train. America's most visible turbine passenger train was the UAC Turbo Train, operated by Amtrak, and before that, by private railroads in the late 1960s. This was a radically different design from anything else running on American rails. A lightweight, articulated train set with aircraft-derived turbines and a tilting mechanism designed to allow higher speeds through curves. The Turbo Train represented American engineering's attempt to leapfrog directly to high-speed rail without the massive infrastructure investments that European and Japanese railroads were making. The design used small, powerful turbines similar to those found in helicopters and business jets. The train set was articulated, meaning the cars shared trucks, instead of each car having its own, which reduced weight and improved ride quality. The tilting mechanism allowed the train to lean into curves, reducing the centrifugal forces felt by passengers and theoretically allowing higher speeds on existing track. On paper, the concept was brilliant. In practice, it was troubled from the start. The Turbo Train entered service in 1968, and while it looked futuristic and occasionally achieved impressive speeds, it was plagued by mechanical problems. The turbines, designed for constant speed operation in aircraft, struggled with the variable power demands of railroad service. The tilting mechanism was complex and frequently malfunctioned. The lightweight construction, while good for acceleration, made maintenance difficult and led to structural fatigue issues. Amtrak inherited the turbo trains when it took over intercity passenger service in 1971 and operated them primarily between New York and Boston, and later on other northeastern routes. The trains developed a reputation for being fast when they worked, but reliability was never better than marginal. Passengers enjoyed the smooth ride and modern amenities, but the trains spent as much time in maintenance facilities as they did carrying passengers. The Turbo Train's most lasting contribution wasn't its performance, but rather the lessons it taught about high-speed rail in North America. It demonstrated that existing track, even when well-maintained, wasn't suitable for sustained high-speed operation. It showed that lightweight construction had to be balanced against durability, and it proved that turbines, while powerful, weren't the miracle solution to America's passenger rail challenges. The Turboliners, RTG and RTL, the final major turbine passenger program, involved the Turboliner family of trains, derived from French designs and operated both in Europe and North America. These trains represented a more conservative, practical approach to turbine technology than the experimental turbo train. The French RTG Turboliners were developed for Trans-Europe Express service in the 1970s, providing high-speed connections between major cities on routes that weren't electrified. They were conventional in layout, with turbine power cars at one or both ends and unpowered passenger coaches in between. The design prioritized reliability and passenger comfort over outright speed, though they were still capable of 140 kilometers per hour or faster. Amtrak purchased American-built versions called RTL Turboliners for service in the Midwest and Northeast. These operated primarily in New York State and on routes radiating from Chicago. Compared to the UAC Turbo Train, the RTLs were more reliable and easier to maintain. They were also more fuel efficient, using modern turbines designed specifically for ground transportation rather than adapted aircraft engines. But the Turboliners faced the same fundamental problem as all turbine trains: fuel economics. When they were ordered and delivered in the early 1970s, oil was cheap and turbines seemed cost-effective. But the oil crises of 1973 and 1979 changed everything. Fuel prices quadrupled, then continued rising. Suddenly, the Turboliners' appetite for expensive jet fuel made them economically unviable. They were more efficient than earlier turbines, but they still couldn't compete with diesel locomotives or, on electrified routes, with electric trains. Amtrak continued operating some turboliners into the 1990s, and even conducted a rebuilding program designated RTL-2, which modernized the trains with more efficient turbines and updated passenger amenities. But by then, the writing was on the wall. Turbines had had their chance, and the economics simply didn't work. The last turboliners were retired in the early 2000s, ending America's experience with turbine passenger trains. The turbine dream didn't collapse suddenly in a single dramatic failure. Instead, it faded gradually as an accumulation of problems eroded the technology's advantages. Each issue alone might have been manageable, but together they formed an insurmountable barrier to long-term success. Let's examine the specific factors that doomed turbine trains. Fuel, consumption, and economics. The most fundamental problem was fuel consumption, and it wasn't a simple issue. Turbines are actually quite efficient under specific operating conditions: high power output, sustained operation, minimal throttle changes. In these circumstances, turbines can match or even exceed the efficiency of diesel engines. The problem is that these ideal conditions rarely exist in railroad operations. Gas turbines achieve their best efficiency when the turbine is spinning at high speed and producing substantial power. The thermodynamic cycle that powers a turbine works most effectively when there's a large difference between the temperature and pressure of the exhaust gases and the ambient air. At full throttle, hauling a heavy train at line speed, turbines perform admirably. But railroad operations require far more than just full throttle running. Consider a typical freight operation. The locomotive starts from a dead stop, requiring maximum power but at zero speed. This is exactly where turbines are least efficient. The turbine must spin up to operational speed before producing useful power, wasting fuel during the acceleration phase. Once the train is moving, there are speed restrictions, grade changes, curves requiring reduced speed, and eventually, a stop at the destination yard. Throughout all of this, the turbine continues consuming fuel, often at shockingly high rates during low-power operations. The idle fuel consumption was particularly devastating. A diesel locomotive at idle consumes relatively little fuel, perhaps 1 or 2 gallons per hour. A gas turbine at idle could burn 10 or 15 gallons per hour, sometimes more, because the turbine must maintain minimum rotational speed even when producing little useful power. For freight railroads, where locomotives might spend hours idling in yards between runs, this was economically catastrophic. Passenger trains faced similar issues. Turbine trains achieved impressive speeds on open stretches of track, but they also made frequent stops at stations. Each stop meant a period of low-power operation followed by hard acceleration, exactly the operating profile where turbines performed worst. The fuel savings from higher cruising speeds were often negated by the fuel wasted during stops and starts. All of this might have been acceptable when oil was cheap, and in the early years, it was. Union Pacific could burn low-grade bunker fuel that cost almost nothing. The French could justify turbine operations based on avoiding electrification costs. But the oil crises of the 1970s changed everything. Between 1973 and 1980, fuel prices increased by factors of 4, 5, even 6 in some markets. Suddenly, the operational costs of turbine locomotives became unbearable. Railroads tried various solutions. They experimented with different fuels, from diesel to kerosene to specialized blends. They modified operating procedures to minimize idle time. They developed automatic shutdown systems. But none of these measures could overcome the fundamental thermodynamic reality. Turbines work best in applications with sustained, high power output, and railroad operations rarely provide those conditions for extended periods. Noise. If fuel consumption was the economic killer, noise was the social and operational killer. Turbine locomotives and trains were loud. Not just loud, but extraordinarily, penetratingly, impossibly loud. The sound of a gas turbine at full power is dominated by the same high-frequency scream that characterizes jet aircraft. This isn't just an annoyance. It's a fundamental property of how turbines work. Union Pacific's big blows earned their nickname not from their size, but from their sound. When a turbine locomotive was operating at full throttle, the noise could be heard for miles. Railroad workers near the exhaust needed hearing protection even for brief exposures. Communities along Union Pacific's routes complained about the noise, particularly during night operations. The sound was so distinctive that people could identify a turbine-hauled train by ear long before it came into view. For freight operations in remote areas, noise was merely a problem. For passenger operations, particularly in urban and suburban areas, noise was absolutely disqualifying. The turbo trains and turboliners operating in the northeastern United States faced constant complaints about noise at stations and along rights-of-way. Communities that might have welcomed faster, more frequent train service were repelled by the screaming turbines. Noise regulations, which became increasingly strict through the 1970s and 80s, made turbine passenger operations difficult or impossible in many areas. The French encountered similar issues with the TGV 001. While the train was acceptably quiet at moderate speeds in rural areas, operations at full speed or in populated regions generated unacceptable noise levels. This was one of several factors that convinced French national railways to pursue electric high-speed trains instead of turbines for production service. Engineers tried various noise reduction measures. They designed sophisticated exhaust systems with baffles and mufflers. They experimented with different turbine configurations and enclosures. They studied sound-absorbing materials and active noise cancellation. Some of these measures helped, but none could eliminate the fundamental problem. A turbine expels exhaust gases at extremely high velocity, and high-velocity gas flow generates noise. It's physics, and there's no way around it without sacrificing efficiency. Heat and exhaust. Closely related to the noise problem was heat. Gas turbines generate extraordinary amounts of waste heat, far more than diesel engines of equivalent power. The exhaust gases leaving a turbine can exceed 1,000 degrees Fahrenheit, hot enough to ignite flammable materials, warp metal structures, and create serious safety hazards. Union Pacific's turbines were notorious for trackside fires. The superhot exhaust could ignite dry grass, wooden ties treated with creosote, and any debris near the tracks. In the arid western states where these locomotives operated, this was a constant concern. Railroad crews had to be vigilant about vegetation management along rights-of-way. Special fireproof materials were installed near turbine exhaust outlets. Still, fires occurred with frustrating regularity. The heat also created problems for the locomotives themselves. Components near the turbine required special heat shielding and insulation, adding weight and complexity. Maintenance workers had to wait for turbines to cool before performing many service procedures, extending downtime. The extreme temperatures accelerated wear on nearby parts and degraded lubricants and hydraulic fluids. Passenger trains faced additional challenges. The turbine had to be isolated from passenger compartments, not just acoustically, but thermally. This required extensive insulation, which added weight and reduced the available space for passengers. Ventilation systems had to work harder to keep passenger areas comfortable. The turbo train's lightweight construction made heat management particularly difficult, as there was less mass to absorb and dissipate thermal energy. In hot climates or during summer operations, the heat problem was compounded. Turbines produce the same amount of waste heat regardless of ambient temperature, but that heat is harder to dissipate when the outside air is already hot. Cooling systems for the locomotive's electrical and mechanical components had to be oversized, adding more weight and consuming more of the turbine's power output. Maintenance complexity. Diesel locomotives are mechanically complex machines, but railroad maintenance crews learned to service them effectively. Turbines, however, required entirely different skills and equipment. This presented a massive operational challenge that many railroads underestimated. Gas turbines are precision machines with extremely tight tolerances. The turbine blades must be perfectly balanced and precisely aligned. The combustion chamber requires specialized materials and careful maintenance. The control systems, even in the mechanical era before electronics, were complex and required expert adjustment. Railroad maintenance facilities, set up to handle steam locomotives and then diesels, were often poorly equipped for turbine service. The turbines themselves were also vulnerable to environmental contamination in ways that diesel engines were not. Dust, sand, and particulate matter ingested into the turbine could damage the compressor blades, reducing efficiency and eventually causing mechanical failure. The western routes where Union Pacific operated its turbines were particularly problematic in this regard. The arid climate created dust storms and persistent airborne particulates. Filtration systems helped, but couldn't completely eliminate the problem. Foreign object damage was another constant concern. Even small debris ingested into a turbine could cause catastrophic failure. A small bolt, a piece of track ballast kicked up by passing wheels. Even a large insect could damage turbine blades. Diesel engines are far more tolerant of such insults. This vulnerability meant turbines required careful inspection after every run, and any sign of damage might necessitate a complete turbine removal for repair. The specialized nature of turbine maintenance created logistics problems. Parts couldn't be sourced from generic suppliers. They had to come from the turbine manufacturer, often with long lead times. Skilled technicians were in short supply, and training new personnel was expensive and time-consuming. When a turbine locomotive broke down, it might be out of service for weeks while waiting for parts or expert service, whereas a diesel could often be repaired in days or even hours. Union Pacific eventually found that, despite the theoretical advantages of fewer moving parts, turbines actually required more intensive maintenance than diesels. The maintenance intervals might be longer, but the work required during each interval was more extensive, more specialized, and more expensive. And when things went wrong, they went very wrong, often requiring complete turbine replacement rather than component repair. The final economic reality. All of these technical problems might have been solvable with enough engineering effort and investment. What ultimately killed turbine trains was simple economics. When comparing the total cost of ownership over a locomotive's expected service life, turbines couldn't compete. Diesel-electric locomotives had continued to improve throughout the period when turbines were being developed. Diesels became more powerful, more efficient, and more reliable. The maintenance infrastructure for diesels was well established, with skilled workers and parts readily available. Fuel consumption, while not as good as the best modern diesels, was still far better than turbines, except under ideal conditions. For passenger service, electrification proved superior wherever traffic density justified the infrastructure investment. Electric trains could draw power continuously from overhead wires or third rails, eliminating fuel costs entirely and allowing for higher sustained speeds without overheating concerns. The initial investment in electrification was substantial, but operational costs were lower, and electric trains were quieter, cleaner, and more powerful than turbines. The oil price shocks of the 1970s delivered the final blow. When turbines were conceived, their fuel costs seemed acceptable or even advantageous. After oil prices quintupled, turbine operations became financially ruinous. Railroads that had invested in turbine technology found themselves saddled with expensive, thirsty machines that consumed profits rather than generating them. By the early 1980s, the verdict was clear. Turbine trains had been a bold experiment, but they had failed the test of economic viability. The technology worked in the sense that turbines could power trains effectively. But effectiveness isn't enough. Transportation systems must be economical, maintainable, and practical for decades of service. Turbines simply weren't. Even as the major turbine programs of the 1960s and 70s were winding down, engineers hadn't completely given up on the technology. Advances in materials, science, computer control systems, and turbine design offered the possibility that the problems that had plagued earlier generations might be solved. Several efforts in the 1990s and 2000s attempted to revive turbine trains with modern technology. None achieved lasting success, but they're worth examining as the final chapter in this story. Bombardier JetTrain. The most ambitious modern turbine train was the Bombardier JetTrain, unveiled around the year 2000. Bombardier, one of the world's leading rail equipment manufacturers, believed that turbines still had a place in high-speed rail, particularly for routes that couldn't justify electrification costs. The JetTrain was designed to prove this point. The concept was compelling. The JetTrain used modern aircraft-derived turbines, far more efficient than the engines from earlier decades. The train set was extremely lightweight, thanks to advances in materials and construction techniques. The power-to-weight ratio was extraordinary, giving the JetTrain acceleration capabilities that surpassed most contemporary trains. Bombardier claimed the JetTrain could achieve speeds of 150 miles per hour or more on conventional track, making it competitive with electric high-speed trains on routes with moderate traffic density. The design incorporated many lessons from previous turbine trains. The turbines were better isolated acoustically, reducing noise to more acceptable levels. Heat management was improved through better materials and more sophisticated cooling systems. The control systems used modern electronics rather than mechanical linkages, allowing for more precise and efficient operation. Bombardier even addressed the idle fuel consumption problem with advanced shutdown and startup sequences that minimized wasted fuel. The JetTrain conducted demonstration tours in both the United States and Canada, visiting potential customers and generating significant media interest. The trains performed well in testing, meeting most of their design specifications for speed, acceleration, and efficiency. Railroad officials who rode the JetTrain came away impressed with the technology and the passenger experience. But, despite these successes, the JetTrain never entered production. No railroad or government transportation agency was willing to place orders. The reasons were complex, but ultimately familiar. Even with modern technology, the JetTrain still consumed more fuel than diesel trains, and couldn't match the efficiency of electric trains on routes that justified electrification. The maintenance infrastructure for turbines remained a concern, particularly in North America, where turbine expertise had largely disappeared after the earlier programs ended. More fundamentally, the JetTrain emerged at a time when the transportation industry was becoming increasingly focused on environmental sustainability. Turbines, regardless of their efficiency improvements, still burned fossil fuels and produced carbon emissions. Electric trains, particularly when powered by renewable energy sources, offered a pathway to zero-emission rail transport. In this context, turbines seemed like a technological dead end, however impressive their performance might be. The JetTrain project was eventually shelved. Bombardier shifted its focus to other technologies, including electric multiple units and diesel-electric locomotives. The JetTrain had demonstrated that modern turbines could overcome many of the problems that plagued earlier generations, but it couldn't overcome the fundamental economic and environmental logic that favored other technologies. Russian turbine locomotives. While Western railroads were abandoning turbines, Russian engineers continued experimenting with the technology into the 2000s and 2010s. Russia's vast distances, extreme climate, and reliance on non-electrified routes in remote regions made turbines at least theoretically attractive. If turbines could work anywhere, it would be on long, straight routes across Siberia with minimal stops and extreme cold that actually helped with cooling the turbine's waste heat. The most notable Russian effort was the GT11H series of turbine electric freight locomotives, developed in the early 2000s. These machines used modern turbine technology combined with electric transmission, similar in principle to the Union Pacific turbines from 50 years earlier, but with vastly improved components. The locomotives were designed for heavy freight service on routes where electrification wasn't economical and where diesel locomotives struggled with the extreme cold. The Russian turbines used advanced materials that could withstand both the high temperatures inside the turbine and the minus 40-degree Fahrenheit temperatures of Siberian winters. They incorporated electronic controls that optimized efficiency across a wider range of operating conditions. Some designs even experimented with hybrid systems that combined turbines with battery storage or diesel generators to handle low-speed operations more efficiently. But even with these improvements, the Russian turbines remained essentially experimental. Fuel costs, even in oil-rich Russia, made turbines expensive to operate compared to diesels. Maintenance remained complex and specialized. And as Russian railways gradually extended electrification to more routes, the market for turbine locomotives continued to shrink. The turbines operated in limited numbers on specific routes, but never became a standard part of the locomotive fleet. Aircraft-derived microturbines and experimental concepts. In addition to these larger programs, various companies and research institutions experimented with smaller turbine concepts through the late 20th and early 21st centuries. Some explored using aircraft-derived microturbines in lightweight rail cars and regional trains. Others investigated hybrid systems that combined small turbines with electric drives and energy storage systems. These experimental concepts often showed promise in laboratory testing or small-scale demonstrations. Modern microturbines are remarkably efficient, compact, and powerful. Combined with battery systems or ultracapacitors to handle acceleration and low-speed operation, hybrid turbine systems could theoretically overcome many of the efficiency problems that plagued earlier designs. But none of these concepts progressed beyond limited testing. The fundamental economics still didn't work. Every analysis reached the same conclusion. Turbine systems, even with modern technology, couldn't match the cost-effectiveness of proven diesel-electric or electric trains. The maintenance requirements, while reduced from earlier generations, remained higher than for conventional locomotives. And the environmental considerations became increasingly important, particularly as governments began implementing carbon taxes and emissions regulations. The final verdict. By the 2010s, it was clear that turbines had lost their final chance to prove themselves in rail transport. The technology had improved dramatically from the 1950s to the 2000s, but so had the alternatives. Modern diesel engines, particularly those meeting stringent emission standards, were far more efficient and cleaner than their predecessors. Electric trains, with advances in power electronics and regenerative braking, could operate with stunning efficiency. And emerging technologies like hydrogen fuel cells and battery electric systems offered the possibility of zero-emission rail transport without the complexity of turbines. The turbine experiments of the late 20th and early 21st centuries demonstrated that the technology could work, that the problems of noise, heat, and efficiency could be managed with modern engineering. But they also demonstrated that good enough isn't sufficient in the intensely competitive and cost-conscious railroad industry. Turbines had to be better than the alternatives, not just comparable, and they simply weren't.